In this video, I will talk about the first few harmonics when one end is closed and the other end is open. So this is the case where I have one end closed and one end is open. Now, practically what that means is on my string, I'm gonna have a node here and an anti-node at this point. Now, I talked before in a different video, a node means that the point is never moving at all. The displacement is always zero. Opposite to that, an anti-node is a point that always has the maximum displacement. So if this point is not moving at all, then this point of the string needs to be going at the highest point and then at the lowest point compared to every any other point on the string. Now, in the same, so, and this is, I'm gonna make a note, this is the first harmonic, this is the second harmonic, and this is the third harmonic. The process, I'm gonna show you the process for drawing these harmonics, and then the process for the rest of them is gonna be the same. Just follow my process. The way that I will think about this is the following. As I said, I know that here I have a node, here I have an anti-node. So I'm gonna start from my sinusoidal wave, this one. And I'm gonna start, since I need a node here, I'm gonna start from a node, here it is, and I'm gonna start moving to the right until I hit a point where I have an anti-node, a point that I have the maximum displacement. So starting from here, that's my node, I need to find the shortest portion of this that includes a node at the left and an anti-node on the right. So if I see here, if I keep moving to the right, the displacement here increases, and then it starts decreasing. Here is where I have the maximum displacement. So I'm gonna take this portion of my wave from here to here, and I'm gonna stretch it, and I'm gonna make sure that it fits here. This is what the first harmonic looks like when you have a closed end and an open end. This point of the string, this point of the string goes from here to here and then up and down, up and down. This point of the string goes up, stops here, and then comes down and goes here and goes up and down, whereas this point goes all the way at the maximum displacement and then down and up and down. This is what the first harmonic looks like. Now, I can talk about the wavelengths later. I'm gonna follow the same process for the second harmonic. Since I need a node on the left, I'm gonna start again from here, and I'm gonna pass this part. I already used this for the first harmonic, and I'm gonna stop on the next one where I have an anti-node on the right. So I start from here and I see, okay, this is where I have a maximum displacement. I'm done with that. And then I keep going, and I'm gonna stop here. Now I can take this portion of my wave, okay? So a node here and an anti-node here. So I'm gonna fit, let's see if I can do it. All right, so there you go. This is the node, this is the anti-node, and what this harmonic will look like when the string is vibrating on this harmonic, this is what it will look like. Up and down, up and down. Here you have a node. This is a node. This point is never going to move. and I have an antinode here and an antinode here as well. Now, for the third harmonic, I'm gonna do the same thing. Since I need a node here, that's a node, this is a node. Starting from here, that was my first harmonic, that was my second harmonic. I'm gonna start from here and now stop here. I'm gonna take this portion. This is first harmonic, second harmonic, third harmonic. Let's see if I can do this. So I need to maybe not. Let's see if I can stretch it. All right, there we go. It looks okay. And this is what my third harmonic looks like. And again, this is a node, and this point here on the string, this is an antinode. This is always moving at the maximum displacement, and also this is an antinode here as well. Now, I also need to think about the wavelength of these harmonics, and I'm gonna work on that here. Let's say the length of the string is L. It's the same string, always the same string, so the length is always L. For the first harmonic, I have the length of the string. Now I need to think, what portion of lambda, what portion of the wavelength do I see here? Well, let's go back to my picture. From here to here, this is one entire wavelength. Okay, from here, from this point to this point is one lambda. Now you can see what I have here is from this point to this point, and since from here to here it is half, I have half of the half, I have 1/4. So the length of the string is lambda over 4, or the wavelength of this first standing wave is 4L for the first harmonic. For the second harmonic, again, I have the length of the string. Now I see I kept, this is lambda, from here to here this lambda, and I took most of it. I left 1/4 out, so the length of the string is 3/4 lambda, which means lambda is 4/3 times the length of the string. And for the third harmonic, go here, I see that I have, that's half, another half, so I have one entire wavelength and 1/4. That means I have 5/4 lambda, and the wavelength is 4/5 times the length. And these are the relationships between the wavelength and the length of the string for the first three harmonics. If you want to find out the relationship for the fourth harmonic and the fifth harmonic, in this case, then what I would like you to do is draw the fourth and the fifth harmonic with the same process that I used here, and then look at the relationship between L and lambda, how many wavelengths you have in the length of the string, and that way you will discover the relationship between the wavelength and the length. So this was the case where a standing wave, when one end is closed and one end is open.